Hello all, welcome to the part C of lecture 13. In this video, I'm going to talk about how to model non-monotonic relationship between the x and y using R. So first, I'm going to create a script. All right, so first what I will do, I will set it's going to be a simulation study. So I'm going to put some number, maybe I'll just draw a sample, random sample between 1:2000 and 1. Okay, 906. I'll put 906, and then maybe I will just simulate 200 sample. Okay, so number of samples that I will simulate. Then I'm going to simulate x, or I will just create a sequence of number between minus pi and pi. So pi is already there, value of pi if you just say, and length gth dot out equal to capital N. So if I just run this, then x will be like 200 values between minus 3.141 and 3.141. So between minus pi and pi, there are 200 grids have been created. Now what I'm going to do is I'm going to simulate some random numbers. I will call it E, or I'll say basically these are going to be my residuals or norm. How many samples? N samples with mean equal to 0, and I'm going to say SD equal to 0.3. Okay, now Z, this is going to be my latent variable, but for now Z is going to be like 0.01 plus 0.45 times x plus E. Okay, now if I plot x comma z, say PCH equal to 20 and color equal to say purple. If I do that, so this is the simulated values of x and z, and all x values are somewhere between negative pi, minus pi to pi, z values, and they have a straight line relationship as we have done here. So but z is unobserved, z is latent variable. So what I'm going to do, I'm going to simulate the y's. Okay, so y equal to z. Okay, first I'm going to define the y equal to z, and then I'm going to say that if z is greater than 0, you say 1. If z is less than equal to 0, then y is 0. Now y are all either zeros or 1. Okay, now so y is the observed response. So now I'm going to define the data set D with x and y only. Define data set D with x and y only. We pretend as if we never saw Z. Okay, now what I'm going to do is D equal to cbind dot data dot frame x comma y. Okay, and now if you just say head of D, so these are my x values and these are my y values. So y values are 0 or 1. All right, now I'm going to fit a GLM, say sigmoid, I will just say model 1 is GLM y tilde x comma data equal to D, and I have to say family equal to binomial link equals to logit. Okay, now if you do summary DL1, so what is happening is you see the coefficient of x is statistically significant. It's very small p-value, z value is very high, so we can say that as n it's positive, so probability of y equal to 1 keep increasing as x value will keep increasing. Okay, fine. Now what I'm going to do, I'm going to make some y hats. Say predict the model data equal to D and type equal to response. So first I'm going to make some points x comma y hat. Okay, x comma y hat, oopsie, sorry about that. So what I have to do is what I will do, I'll just copy this, I'll put it here, and x and y, and then points are like this. You can see these are the true actual x and y's. When I'm doing it, it's actual x values and the y values. Y is all I'm taking at the 0 and 1, and if I put the points x and y hat, and then I'll be doing like PCH equal to 20 with color equal to red. Wonderful. So now it's nicely sigmoid curve, a nice sigmoid curve. And if the, remember that if the underlying relationship is a straight line, then this nice sigmoid curve will work out very nicely. Okay, but what happens if the underlying relationship not necessarily has to be, straight line? That time we may have a bit of a different situation. So beyond non-monotonics, and sigmoid means it's basically the true relationship will be always non-monotonically increasing function. So beyond our sigmoid curve, so we want to go beyond sigmoid and sigmoid curve and model non-monotonic relationship. Okay, so how we do that? Set dot. So what we will do, we will just copy this part, just bring it here, and this is my old model, and I'm going to change this model to completely different model, sin x. Let's see what happens. Okay, can it model? So this is my y and x, z, plot x comma z. If I plot x comma z, ch equal to 20, color equal to purple. Okay, so this is the relationship between x and z, but we are not seeing the z. This is the true relationship, completely non-monotonic behavior, but we don't see the thing. Okay, so if this is the situation, and then what we can do, we can do the create the y's exactly the way we want, so the y's are now all initially few ones, zeros, and then ones, some zeros, ones. So yeah, so it is not that straightforward. Okay, now we are going to define the xy, and we will going to pretend as if we have not seen the z, the underlying, all we have the data x and y, right? So now we have that. Let's try to model make the second model. Let's make the second model. Okay, if I make the second model, now you see second model also the x is sort of statistically significant, so that means we are in a good shape. And if we want to have the plot this, we want to plot this. Now clearly we have some data points here, some points here, some points here, and some points here, whereas our points, now we have to have a y hat predict. So let me just take this y hat predict, and instead of model 1 I need model 2. Let me just run the y hat predicts through, and it's a constantly non-increasing. These points looks like does not have that much of effect, so it's going to be a straightforward model. However, now what we are thinking is, can we do some non-linear, non-monotonic feature engineering with for non-monotonic relationship, Okay, so model 3, and then I'm going to let's take this model directly, and then plus ix plus ix squared Actually this should be square and this should be cube. Okay, and if you see summary of model 3, summary of model 3, what we are seeing that coefficient for x and coefficient for x cube are statistically significant. So what I can do, we can just even actually do a step function that will do a stepwise correction, stepwise selection. It will run, and if I do a stepwise selection, it will make the model with only x and x cube. That is my best model. And then what we can do, we can do a prediction based on model 3, and then now we can plot actually now if I do this, so this is the predicted values, and now if I just do the blue, let us do into so this model, so these predictions, this capturing the cubic relationship between x and y, this model is capturing the cubic relationship between x and y, whereas so non-monotonic, there is a because if you look into the real data, there is a sort of a, this is sin x, that model doesn't know. It's when I am giving higher order polynomial, it able to capture that because there are few points here and there, and that's kind of gives you the best kind of fit. So this is really the power of feature engineering that we see. So I am going to share this code in the NPTEL portal. So please have a look, try yourself, try different feature engineering, see how it helps you. Okay, you can try direct sin x, see if you use sin x how good it would be, why not. So good luck with feature engineering on this, but that is how we do in classification, binary classification. So enjoy, see you in the next lecture, next video.